Welcome to the fifth lecture on economics, management and entrepreneurship. If you recall, we had covered demand, supply, market equilibrium in the first two lectures, and thereafter we covered demand elasticity, and in the last lecture we covered demand forecasting. In a way, in the last few lectures, we have covered more on the demand aspects of economics of a firm. Today, we shall discuss on production, the supply aspects of a firm. In this lecture, we expect you to have the concepts of production function, total, marginal and average product, returns to factor and returns to scale, various curves such as iso-quant, iso-cost, iso-revenue and product transformation curves, and the effect of technological change on production. Each one of these concepts we will discuss hereafter. To start with, we discuss about production function. By production function, we mean the amount of production that is produced, amount of products that is produced because of certain factors, certain inputs such as material, labor, capital and so on and so forth. Here we define production function as the maximum possible output that can be produced using a given combination of inputs. It is also the minimum quantity of inputs required to produce a given level of output. Basically, it maps or it defines a relationship between the inputs used and the outputs produced. A very popular production function is Cobb-Douglas production function. It is basically a power function that defines the quantity produced Q as a function of, in this case I have given an example of two input material, two inputs x and y. The relationship that defines Q with x and y is a power function relationship. Q equals A multiplied by x to the power b into y to the power c. And if I take a log transformation of both sides, this becomes ln q, natural logarithmic of q equals ln a plus b ln x plus c ln y. Cobb and Douglas, two economists, had suggested that such a production function covers a very wide range of relationships between products produced and the input material inputs given to a firm. Then we define three types of products: total product, marginal product and average product. By total product, we mean the quantity Q produced by a firm for a given set of inputs, naturally in a specific period of time. That is called total product. Marginal product, on the other hand, is the first differentiation of total product with one of the factors. In this case, I have given an example of only one factor, let us say x is a factor, there can be many other factors. Then the marginal product is given, I am sorry, this should have been MR, this would have been MPX rather than MRX, this would have been MPX is equal to dq dx is the amount by which the total product Q changes for a 1 unit change in the factor, in a factor of production x. So, if it is for another factor of production y, then we write MPy equals dq dy. Basically, this says the amount by which the output Q changes for a unit change in a particular factor of production x. Next is average product AP. This is simply the ratio of the total amount produced by the value of a particular factor x employed, and this is called APX. Similarly, if we have another input y, then APY would be total product TP divided by y. So, these are the three things that we shall be using hereafter. We next talk about returns to a factor, or also known as factor productivity. Returns to a factor or factor productivity is the magnitude of percentage change in the output of a firm when a particular factor of production undergoes a given percentage change. And we show it in this case that as x increases, a particular factor x increases, how the total product Q changes as x increases. Normally, as x increases, initially the rate of change of Q is high, but thereafter it shows a decline, and the rate of increase in Q shows a decline, becomes 0, and then it becomes negative again. This rate of change is basically the marginal product. This should be MPX and not MRX. It should be dq dx. So, the slope of this line is positive and is growing. So, the value is also growing, marginal product value is growing till a point of inflection comes where the value decreases. So, hereafter the value decreases, but still positive, and somewhere here the slope can be negative, meaning that the marginal product becomes negative. So, this shows that as a factor, that is input to production, increases, the amount of production may rise to certain extent, becomes stagnant for some time, and then may actually decline. This is known as the law of diminishing return or law of diminishing marginal returns. If the amount of an input factor is increased while holding all other factors constant, then the marginal product of that factor will eventually diminish. This is basically shown in this particular slide, that keeping all other factors at certain value, if x, one factor x increases, then the amount of quantity produced increases for some time, comes to a steady state value, and thereafter it declines. This is the law of diminishing returns. Next, we give the concept of production isoquants, basically isoquantity produced, that is same quantity produced for what combination of the input materials. We have in this example considered labor and capital as the two input materials for production, and this particular one curve for Q1 let us say, and this curve is for Q2. It means to produce a quantity Q1, different combinations of labor and capital could be used. We could use this labor, a low capital but high labor, or high capital requiring less labor. We may also get the same quantity produced. So, this is the iso quantity or isoquant curve, meaning that for different combinations of y and x, or here y and x, we could get the same value Q1. Whereas, this is an example of another quantity produced, which is Q2, and Q2 can be achieved for different capital and labor, different capital, but these two curves are parallel to each other. This is called production isoquant curves. This is a curve that represents combinations of input factors, in this case x and y, combined efficiently to produce the same quantity of output. This production isoquant is a very useful technique, graphical technique, and we shall be using it very frequently hereafter. As you can see, if you consider any one isocant, say for example, this point on the isoquant Q1 indicates that you need high amount of capital Y and low amount of capital X, and point number 4 requires more labor X, but less capital Y. Now, you will see that suppose you move from 1 to 2, it means you are using more labor, but less capital. Now, consider points 3 and 4. From 3 to 4, you are also using more labor and less capital, but you will realize that the extent of labor force required or labor hour required to move from 1 to 2 is much less than when you move from 3 to 4. The amount of labor required here is much larger, whereas the amount of labor required here is much less compared to the same reduction in the value of capital. That is 1 to 2, the level of capital requirement is reduced by this amount, and the level of capital requirement reduced by this amount, but correspondingly the requirement of labor is much more. This is called substitutability of factors. The amount of additional labor required to reduce capital requirement from point 1 to 2 is much less than that required to reduce capital from point 3 to 4. Such a diminishing substitutability is a feature of most production systems. Firstly, that factors can be substituted, that means you can use more labor and less capital. This is substitution, but as you move along you will see that the amount of substitution required is much more than when it is operating at these points. Now, we come to the concept of marginal rate of technical substitution. Now, here basically we say that it is the slope of the isoquant dy dx. Now, just look at this isoquant, this is an isoquant. Now, it is at any point it has a slope defined by a tangent at any point. So, we would like to, that is nothing but dy dx at that particular point, and this is the slope of the isoquant. It gives a measure of substitutability of one factor for another for producing the same quantity q. As you can see, it has a negative slope, that is what we are writing, it is negative. Basically dy dx is the slope of the isoquant curve and that is negative. Dy dx, as you can see, is equal to, can be written as equal to dq dx divided by dq dy. So, dq dq cancels out, dy goes to the numerator, dx remains in the denominator. So, dy dx can be written as dq dx divided by dq dy, but dq dx by definition is the marginal product, the change in q for a unit change in the value of x. So, this is mpx and this is mpy. Therefore, the rate of technical substitution is minus because the slope is negative, minus the marginal product of x divided by marginal product of y. Now, let us see whether substitutions, how substitutions happen in complements and in other cases. Now, this is a case of perfect substitution. An example that we have taken is electric power generation. In electric power generation, it can use either oil or it can use gas. Now, here the isoquant curve is basically a straight line, and for a higher value of electricity generated, it is Q2, it is parallel to the Q1 isoquant line. So, here we see that if I draw a line here like I did in the case of, in this case, this requirement is much less than this requirement. When it is a straight line, it will be exactly the same. So, we can this is a case of perfect substitution by gas with oil or vice versa. But if we consider the case of complements, please recall that a complement is one which says that this is a case of a car. In a car, if we need one frame, we will need 4 wheels. This is a perfect complement. If we use 2 frames, that is for 2 cars, we need to have 8 wheels. The quantity produced is 1 car here and the quantity produced is 2 cars here. So, this we see there is no substitution here, and here is a case of perfect substitution. Now, we bring in the concept of iso-cost curve. For that, this will be required to know the least cost combination of factors. That means, we can find out at what combination, what price combination of factors the quantity produced is maximum. Let the unit prices of the factors of production be P x and P y. P x is the unit price of input x, P y the unit price of input y. Therefore, the total cost of the inputs will be unit price P x multiplied by the amount of x used plus the unit price of input y into the amount of input y. That is the total cost of input. Now, we can draw we can find out, you can draw a iso-cost curve and whose slope is actually it should be dy dx, which is nothing but del T c del x c, partial differentiation of T c with respect to x and partial differentiation of T c with respect to y, and that is nothing but, if I take partial differentiation of T c with respect to x, I get the unit price P x, and partial differentiation of T c with y, I get unit price P y. Therefore, dy dx is nothing but the ratio of the unit price of x to unit price of y. Incidentally, at the equilibrium, dy dx is nothing but dq dx divided by dq dy, which is same as dy dx, and this is the marginal product of x m p x and this is m p y. Therefore, the iso-cost curve at the equilibrium will be equal to the marginal rate of technical substitution. This is shown here in this curve. As before, we have the input x here and the second input y here. This is the isoquant curve for quantity q 1. This is isoquant curve for quantity q 2, and we are assuming that q 2 is higher than q 1. Now, this is a particular iso-cost curve having a slope equals unit price P x, it is basically dy by dx, and at this particular point the slope of the isoquant curve is also dy dx. Therefore, at this point the slope of the isoquant curve and equals the slope of the iso-cost curve. So, this is the iso-cost curve, and for a higher price, higher amount, higher price, this is another iso-cost curve, and ratio remaining same, they are parallel. So, this is Px by Py and the basically dy by dx. So, isocost curve is tangent to isoquant curve. This is the point of equilibrium. Now, movement from one isoquant, that is from Q1 to another isoquant Q2, shows a change in the scale of operation. So, when we increase from one particular amount of production Q1 to a higher level of production Q2, it means that our scale of operation has increased or that the company has expanded. This is also called expansion path. It has shown a different or an increased scale of operation. This is what we are now talking next, which is returns to scale. Returns to scale is the magnitude of percentage change in the output of a firm when each factor of production undergoes a given percentage change. That means, if both x and y are given equal percentage change, then what is the change that happens in the output of the firm? This is given by returns to scale. Returns to scale is also called expansion path. Returns to scale of a production system describes the increase in output resulting from a proportionate increase in all inputs, just as I had told, proportionate increase in all inputs. Now, if the percentage increase in output is greater than the percentage increase in inputs, then it is a case of increasing returns to scale. That means, if let us say we increase all inputs by 10% and we see that the output rises by 15%, this is a case of increasing returns to scale. Whereas, if the percentage increase in output is equal to the percentage increase in inputs, then it is a case of constant returns to scale. If by giving a 10% rise in the value of all inputs, we see that there is a 10%, more or less 10% rise in the output, then we say it is a case of constant returns to scale. And lastly, if we see that by giving a 10% increase in all input factors, the output reduces by less than 10%, say for example 5% or 7%, then it is a case of decreasing returns to scale. Now, this returns to scale can be described in different ways. Firstly, graphically. Graphically, this is our expansion path for a constant returns to scale. That means, if x and y are given equal percent change, then q rises in the same proportion. So, this is a straight line, that is the constant returns to scale. Increasing returns to scale for a change in x and y, q rises in a much bigger fashion, whereas here it is less. This is a case of decreasing returns to scale. So, graphically one can depict returns to scale, the three types, constant, increasing and decreasing returns to scale, in different ways. Of course, it is possible that one can have or a firm can experience what is known as variable returns to scale, which means that as x and y changes, q may initially rise in an increasing and thereafter decreasing and then may go down, becomes like this. Then we say that it is a case of variable returns to scale. Or VRS. CRS for constant returns to scale, IRS for increasing returns to scale, and DRS for decreasing returns to scale. Now, this is explained here in another way. It says that as before, this is y and this is x axis. These are isoquants for quantity q1 and q2. We are assuming q2 higher than q1, and here we are saying suppose that the firm is operating at this point, giving an input x1 and the other input y1, getting q1, and suppose that x1 rises by a fraction f, meaning x2 is equal to 1 plus f into x1, and y2 y also increases by a fraction f, meaning y2 equals 1 plus f into y1. Then the value of production q2, how it is related with q1. Suppose we find that q2 also rises by this same fraction f, that is q2 is equal to 1 plus f into q1. That means, the rise in q2 is f of q1 by the same fraction f as the input, each input was raised. Then we say that it is a case of constant returns to scale. Whereas, if we find that q2 is higher than 1 plus f into q1, then it is a case of increasing returns to scale. Whereas, if we find that q2 is less than 1 plus f into q1, then we say that it is a case of decreasing returns to scale. This we now illustrate with the help of Cobb-Douglas production function. Recall that Cobb-Douglas production function is a power function. Q equals A into x to the power b into y to the power c. Taking natural logarithmic, we get ln q equals ln A plus b ln x plus c ln y. We can write from here dq by q equals b into dx by x plus c into dy by y. Now, this dq by q is the fractional change of in q, dx by x is the fractional change in x, and dy by y is the fractional change in y. Now, since all factors are increased by the same proportion f, the following will hold, that is dx by x and dy by y will be equal to f. If it is so, then what is dq by q? dq by q will be equal to b multiplied by f plus c multiplied by f, which is nothing but b plus c whole into f. So, this also gives another way to define whether the returns to scale is constant or increasing or decreasing by comparing b plus c with 1. So, from here we say that if b plus c is equal to 1, then dq by q is equal to f, same as the proportional change or fractional change that we had given to each of the inputs. Then it is a case of constant returns to scale. Whereas, if b plus c is greater than 1, then this whole quantity is greater than f. It means that for a change in f, change in x and y by amount, fractional change in x and y by an amount f leads to a higher than fractional higher value to the fractional change in q by more than f. So, this is b plus c greater than 1, it is a case of increasing returns to scale. B plus c less than 1, it is a case of decreasing returns to scale. Please note that b and c are nothing but exponents in the production function. Therefore, merely by looking at or summing the values of b plus c, we can say whether the firm is operating in an increasing returns to scale or a decreasing returns to scale. If we find that b plus c is more than 1, then there is a chance, there is a high probability that by increasing the amount of input, we get more than proportionate increase in the value of q. Whereas, if we find that b plus c is less than 1, it means that if we increase x and y by some amount, equal amount, there will be less than proportionate increase in the value of q. This information is very important in deciding how much more input we should give to increase our production. Now, we come to output elasticity and relate it to returns to scale. Output elasticity is epsilon q is the percentage change in output associated with a 1% increase in all inputs. We define this as epsilon q as equal to del q by q, percentage change in output divided by del x by x, where x represents all inputs put together or added together. So, del q is equal to del q by del x multiplication, x goes to the numerator, x by q. Now, if epsilon q is greater than 1, then also it is a case of increasing returns to scale. If epsilon q is equal to 1, then it is a case of constant returns to scale. If epsilon q is less than 1, it is a case of diminishing returns to scale. This we say merely by understanding that we have defined epsilon q, the output elasticity, as the percentage change in or the fractional change in q for a fractional change in x. Now, we talk about product transformation curve. Here, this curve is relevant when a firm is producing 2 or more products. In this case, we are considering of course only 2 products, product 1 and product 2 we are considering, and the product transformation curve basically shows the locus of combination of outputs for a given input. Suppose that we are spending so much money in our input, labor, capital, material and so on and so forth, then we can produce different quantities of product 1 and product 2 for the same input. So, this is using the same input, different combinations of product 1 and product 2 can be produced. For example, let us say by using 10 lakh rupees, we could produce this amount of product 1 and this amount of product 2, or we could produce more product 2 and less product 1. And if we spend more on input, instead of 100 lakh, suppose that we spend 200 lakh, then we could produce more of product 1 or more of product 2, but the curve will be a higher curve. So, this is called a product transformation curve for different inputs. I have drawn 2 curves. This is for lower amount of input, this is for higher amount of input, but input is constant here. The curve shows the locus of combinations of outputs for a given input. The curve is downward sloping, the slope is negative and becoming more and more, because an increase in output of one product, suppose I increase an output from here to here, then it decreases the output of the other. So, the curve is negative, the slope is negative and therefore, it is moving downward sloping. For higher input, the curves are like this. So, this is the product transformation curve. Now, we saw iso revenue curve. Now, if each product has got a particular price, then we can realize some revenue by selling different amount of material. That is, if the price is P1 for product X1 or Q1, then P1 Q1 plus P2 Q2, that is the revenue. So, this could be one revenue, and for higher revenue can be realized if we have more products manufactured, product 1 and 2. Now, this diagram shows that we can decide from a product transformation curve and the iso revenue curve what should be our optimal mix. That means that if this is the iso revenue curve and this is the, if our unit price for product 1 and product 2 are given, then their slope will decide the slope of this line, and that slope and the slope of the product transformation curve must be equal to decide the point at which the optimal product mix will be achieved. That means, if I operate at this point, that means if I produce so much of product 1 and so much of product 2, then I will realize the maximum revenue out of producing and selling these goods. If however, I produce this much product 1 and this much product 2, then my revenue will be much less, parallel to this line going here. So, this is an example of deciding how or how much of product x 1 and how much of product 1 and how much of product 2 should be produced, given their unit selling price. Now, we talk about technological change and its effect on production. As you know, technological change is the order of the day, and production is getting affected as time progresses, as new technology is coming. Now, technology can influence production in basically two ways. One, by a change in the process or a change in the product. When we talk about process change, we are saying that we are able to achieve the same output with less input. That means, the productivity is high. However, when we are bringing in a product change, it means with the same input we are able to produce more output. Now, this is shown in the form of two figures here. Now, here we are showing this is a isoquant for the input material x and input material y, and this, let us assume, is the present operating condition of a farm using input x and input y. We are able to get the same quantity for different combinations of x and y. Now, if a superior technology is available, then this curve will shift to its left, meaning that we will be able to produce the same output, but with less amount of x and less amount of y. This curve will shift to the left. Whereas, if it is a case of inferior technology, another farm using an inferior technology will experience an isoquant curve, which will be on the right side of this, meaning that it will be somewhere here. For the same quantity q, it will require more x and more y. This is the case of process change. Now, let us consider the case of product change. Now, this is look at the axis, this is q 1, the quantity of product 1, and this is q 2, the quantity of product 2. So, this is a case of product transformation curve. Now, in the product transformation curve, we for the same input, we are saying that given the same input, we are able to produce different types of mix of product. different product mix, meaning different values of Q1 and Q2 are produced for the same input. Now, if we are using superior technology, then with the same input the product transformation curve will move to its output, indicating that we are able to get more output for the same input. Whereas, a firm using inferior product technology or product design will have a product transformation curve that will be moving to its left, meaning that for the same input output will be less. Now, technological change is a vast area and lot of studies have been made in this area, and we have not discussed them here. So, if I summarize what we discussed today, to start with is that the quantity produced in a company is a function of various input factors, and our interest was to decide or to find out if we increase one factor, how much change is happening in our quantity produced. If we increase all factors by the same amount, how much change is happening to production, and we are defining them as returns to a factor or returns to scale. After that, we consider the effect of technological change on production. Well, these 5 lectures we have devoted to general economics, microeconomics, and the remaining lectures we shall spend on more operating decision making principles of economics, in particular costing, accounting, and similar such things that will be useful in managerial decision making. Thank you.